Welcome to the deep dive. We take your sources, peel back the layers, and really get to the core insights you need. Today, we're digging into something fundamental in high-performance chips, the architecture of the AMD Versal adaptive SoC. You know, for years, it was all about Moore's law. Smaller transistors meant faster chips. Simple. But, well, that's not the whole story anymore, is it? The real bottleneck, the thing slowing us down now, it's actually moving data across the chip. Those interconnects, the delays are just ballooning, almost quadratically.
Yeah.
Getting data from A to B is the new big challenge.
That's absolutely right. And it's forced a real rethink in silicon design. A Versal adaptive SoC is a prime example. Instead of just using the standard programmable logic for everything, which gets tricky for timing over long distances, AMD put in a dedicated hardwired communication system.
The hardened network on chip, the NoC. And you're saying this isn't like older soft NoCs built from logic blocks. This is actual dedicated silicon.
Exactly. Hardened. Purpose-built. It lets the chip tackle those physical layer problems head-on. Think optimized wiring, repeaters, stuff needed for these huge multi-die, multi-SLR devices. So for you, the designer, it means shifting your thinking. You're not just wiring points together anymore. It's more like managing a packet-based network on the chip itself, connecting your IP, your PL, PS memory blocks.
Like a little internal internet almost. So how is this network physically laid out? Is it like dedicated lanes on a highway?
It really is. Think of it like a roadmap, yeah. And knowing that map is critical, there are two main physical pathways or planes: the horizontal NoC, HNOC, and the vertical NoC, VNC.
Okay, HNOC first. Horizontal sounds like maybe the fast lane.
It generally is. The HNOC runs, well, horizontally across the chip. It's typically set up for the really high-speed stuff like DDR memory, HBM. And yeah, because of how it's laid out, it tends to have lower latency. It's the preferred route if you can use it.
Okay, so then the VNOC. Vertical sounds like maybe the crosstown route that you sometimes have to take.
Pretty much. It's essential in these big chips, especially the multi-die ones. The VNC runs vertically up and down the height of each SLR. Those are the big logic regions on the chip. And in devices with stacked silicon, the VNOC is what bridges between the different dies using something called the NoC interdie bridge. You need it for full chip communication.
But wait, if they went to all the trouble of hardening this NoC, why is there such a big performance difference between horizontal and vertical? That seems counterintuitive.
Well, it's largely a physical reality. Crossing between those SLRs spanning the full height of the chip, it just takes longer. And the sources we looked at really highlight this trade-off. It's quite stark, actually. The VNOC can have 2 to 3 times higher latency compared to the HNOC.
Whoa, okay.
Yeah.
2 to 3 times? That's huge. If my application is latency sensitive, like say financial trading algorithms or real-time video processing, accidentally getting routed onto the VNOC could completely blow my timing budget.
Absolutely. And it's not just latency. You could also see a bandwidth drop, potentially up to 50%.
50%.
Yeah.
Just from hopping across an SLR boundary.
Just one hop, yeah. So this single fact forces the designer, especially for high-performance stuff, to become a physical planner. You have to know where your data is flowing, HNOC or VNC. If you don't, you're basically gambling with performance.
Okay, that makes sense. So we have these physical highways. Before we talk about directing traffic, what are the on-ramps and off-ramps, the logical piece?
Right. 3 main building blocks. You've got NoC master units, or NMUs. They're the entry points where data gets onto the network. These come from your processor, your logic, maybe specialized blocks like HBM, different types like NMU 512, or a low latency NMU 128.
Okay, NMUs are the start points.
Then you have NoC slave units, NSUs. Those are the destinations, the exit points.
Makes sense. Masters send, slaves receive.
And connecting them all, managing the routes between potentially many NMUs and NSUs are the NoC packet switches, the MPSs. They're the routers, deciding whether traffic goes on the HNOC or VNC based on the destination.
Right. Managing all those connections sounds incredibly complex.
Yeah.
Dozens of endpoints, multiple SLRs. This must be automated, right?
It has to be, for the most part. That's where the NoC compiler comes in. It's part of the Vivado tool suite.
The unseen architect, as our sources called it.
Yeah, that's a good way to put it. Its job is to look at your design's requirements. What needs to connect to what, the quality of service you need, the bandwidth. And based on that traffic specification, it automatically figures out the best NoC configuration, programs the internal settings when the chip boots up.
Okay, so for basic designs, maybe it just works. Connect A to B, compiler figures it out.
To simple cases, yeah, it can save a lot of time.
But I sense a but coming. What are the limits? If it finds the optimal route, why do designers need to step in?
The but is that the compiler is only as good as the information you give it. The quality of that traffic specification is key. If the spec is vague, just connect these two things without clear performance goals. The compiler might give you a route, but maybe not the best one. Maybe it puts latency-sensitive traffic on the VNC because it looked easier initially. We've even seen research showing it can sometimes fail to route a network much smaller than the chip can actually handle if the constraints aren't clear.
So it's not magic. It needs guidance.
Exactly. And this leads to a really important point. The compiler generates its solution before everything is physically placed on the chip fabric.
Ah, okay. So if I, as the designer, add a constraint later that says, this specific logic block must go here, and that block happens to contain an NMU or NSU.
Right. Your later physical constraint might force that NMU to move, and suddenly the compiler's carefully calculated route might be invalid, or just suboptimal. It becomes out of date.
So my manual placement directly impacts the automated routing. There's the link.
That's the crucial link. Automation helps, but physical reality, defined by your constraints, rules. For top performance, you have to use Xilinx Design Constraints XDCs to actively guide the compiler. Tell it the physical realities you need.
Which brings us to the design flows. There's the graphical way, IP integrator, IPI.
Yep, the block diagram approach, click and connect. It's correct by construction, great for getting things up and running quickly. Prototyping.
And then there's the harder path, the modular RTL flow.
That's the manual approach. You actually instantiate the NoC components, the NMUs and NSUs, directly in your Verilog or VHDL code as XPM Xilinx parameterized macros.
Okay, that definitely sounds like more work. Why would a designer choose that harder path?
Control. Fine-grained control. If you need to squeeze out every last bit of performance, avoid that VNC latency hit, the modular flow forces you to define everything explicitly. And critically, it means you must use XDC files to specify connections, properties, and physical placement.
Right, the XDC files. Let's talk about those. What goes in them besides just saying connect X to Y?
A lot, potentially. An XDC file is basically a script written in TCL that applies constraints. These can be logical, like timing, or physical, like location. And a good practice, by the way, is to use separate XDC files for different parts of your design. Don't just dump everything into one giant file. Makes it easier to manage.
Okay, easier maintenance. But here's a practical question. What if I use a pre-built IP core, say, from AMD or a third party? It probably comes with its own constraints. How do I make sure my critical placement constraint doesn't get ignored or overwritten by the IP's default settings?
Ah, excellent question. That's where a powerful TCL property called a processing order comes into play. By default, constraints often have a certain processing order, and IP constraints might get applied later. But you can set this property on your constraint file. If you set it to processing order late for your user XDC file, you're basically telling the tools, my instructions come last and they take precedence. It's how you override defaults for those critical things.
The designer's trump card. Got it. Okay, before we get to the really physical stuff, there's one more logical detail. Address mapping. Sounds like software, but it hits the hardware.
It does, and it can trip people up. The NoC routes packets based on destination addresses, just like a network. But you need to be careful about address widths. What happens if, say, your master unit, the NMU, has a wider address bus than the slave unit, the NSU it's talking to?
Does it just ignore the extra bits?
Essentially, yes. The most significant bits, MSBs, might just get dropped.
Okay, give me an example.
Sure. Imagine a master with a 40-bit address capability trying to talk to a slave that only understands 32-bit addresses. Those top 8 bits from the master, gone. Dropped by the interconnect. So the master might think it's accessing different regions in a huge memory space, but because those top bits are lost, it might actually be hitting the same 32-bit slave range over and over.
Ouch. So you need to calculate the actual reachable address range, considering potential MSB drop.
You absolutely do. It's crucial for getting the memory map right.
All right, this is all setting the stage for optimization. We know the physical paths, HNOC, VNOC. We know we need XDCs for control. Now let's connect our performance demands to the physical chip. Starts with quality of service, right? QoS.
Exactly. QoS is how you tell the NoC compiler about traffic priority. There are 3 main classes defined on the NMU, the master interface. You've got low latency. This is for things that absolutely need to be fast, like maybe CPU cache refills from DDR. Time sensitive.
Okay, makes sense.
Then there's isochronous. This is for traffic with real-time deadlines, like maybe certain video streams. Guaranteed bandwidth, predictable timing.
And the third.
Best effort. This is the default, used for bulk data transfers where maybe latency isn't the absolute top priority, but throughput is. Things like large data moves to or from memory.
Now, I saw something interesting in the source material about that best effort class. It said it's the only option for HBM high bandwidth memory traffic. Why would the highest bandwidth memory be stuck with the lowest priority QoS?
That's a great observation. It seems counterintuitive, doesn't it? But think about how HBM is used. It's all about massive throughput, huge birds of data. The thinking is that HBM traffic is inherently bulk data. Trying to manage it with the fine-grained controls of low latency or isochronous might actually add overhead and complexity, slowing things down. So the architecture essentially says, for HBM, focus on raw throughput using best effort. Let the sheer bandwidth handle it.
Huh. Okay. Prioritizing throughput over granular latency control for HBM makes a certain kind of sense. So I define my QoS class, and I also specify a bandwidth required, say, in megabytes per second. How do I know if the NoC can actually deliver that?
That's where the feedback loop comes in.
Yeah.
You run the tools, including the NoC compiler step, and then you look at the Vivado QoS report. This report is critical. It compares the bandwidth you requested against the bandwidth estimate that the compiler thinks it can achieve with the current routing solution.
So those numbers are way off.
Then you know there's a problem. Either your request is unrealistic for the path chosen, or the compiler couldn't find a good route. It tells you if your goals are even feasible on the silicon as configured.
But like we said before, just asking for high bandwidth isn't enough if the path takes the slow VNC route, right? The QoS setting alone doesn't guarantee low latency if the physical path is wrong.
Precisely. QoS and bandwidth requests are logical. They don't inherently control the physical routing plane.
Which brings us finally to the ultimate tool for controlling that physical path. The physical lock property in the XDC file.
This is it. This is the designer's direct control over the physical silicon. Using PhysicLay, you can specify the exact coordinates on the chip where an NMU or NSU port must be placed. The syntax is something like set property henfig. Physical lock no CNMU 512 X1Y33. You're literally floor planning your network endpoints.
And the reason this is so powerful, if I'm putting it all together, is because it allows you to force traffic onto the preferred HNOC to avoid that VNC penalty.
That's the core idea, yes. If you have a critical low latency path, you analyze the chip layout, figure out locations for the NMU and NSU that are close together horizontally, maybe within the same SLR if possible, and then you use physical lock to lock them down there. By doing that, you make it physically difficult or impossible for the compiler to choose a route that involves the high latency VNOC for that specific connection. You're dictating the physical feasibility.
You're essentially removing the bad option from the table for the compiler.
Exactly. You're using physical constraints to guarantee the logical performance characteristic you need, like low latency.
Wow. Okay, it's a real interplay between the logical needs and the physical reality. Let's quickly recap that modular RTL flow then, because the final check is still needed.
Right. So for that high control path, 1, instantiate your NMU and SU XPMs in your RTL code. 2, create your dedicated XDC file. Put in connectivity, addressing QoS needs, and crucially, those physical lock constraints for critical paths. Remember, processing order late if needed. 3, run the implementation flow, including commands like update nocos, which invoke the NoC compiler.
And 4, analyze the results, primarily using that NoC QoS report. Check the traffic classes, compare bandwidth required versus bandwidth estimate, look at latency estimates.
And this is the critical final step. Remember what that report gives you. The QoS report provides structural estimates. They're based on a static analysis, how long the wires are, how many switches are involved.
Static analysis, meaning it doesn't know about actual real-world traffic.
Correct. It doesn't account for dynamic effects, contention between different data flows, bursty traffic patterns, queuing delays that only show up under load. So for actual design sign-off, you absolutely must validate with real traffic stimulus.
Either through extensive simulation that models traffic accurately, or preferably testing on the actual hardware.
Mandatory. The static report is a guide, maybe even a very good guide, but it's not proof of real-world performance.
Okay, that's a vital clarification. Don't just trust the report and verify with real traffic. So this deep dive really shows a shift, doesn't it? The Versal NoC is this amazing hardened piece of silicon built to solve physical limits. But getting the most out of it means the designer can't just rely on automation. You have to master that connection between the logical requirements, QoS, bandwidth, and the physical implementation using tools like physical lock. You're not just coding, you're architecting pathways on the chip.
You really are. You have to anticipate the physics, anticipate where the default routing might hurt you, and use constraints to guide it correctly.
Okay, to wrap up, let's leave our listeners with something to chew on. A final provocative thought. We mentioned that for the HNOC, the horizontal path, read bandwidth is sensitive to distance, but write and stream bandwidth are largely independent of distance.
That's a fascinating detail from the architecture, yeah.
So think about this. A single physical arc constraint you apply might perfectly optimize a critical read flow by placing endpoints close together on the HNOC. But that same placement might have zero benefit or maybe even a negative interaction for a write flow using the exact same physical NoC resources between those same endpoints, because write bandwidth isn't as distance sensitive there.
Interesting asymmetry.
Right. So if one constraint can have these different impacts on different traffic types using the same path, what does that imply? What deeper complexities emerge when you're trying to juggle multiple high-performance streams, reads, writes, different protocols, all sharing this NoC infrastructure? What's the next step in analysis or design methodology needed to manage that kind of multivariable optimization challenge effectively? Something to ponder.